take a look at that. All right, number one. A stronger oxidizer to weaker oxidizer is a driving force for double replacement reactions. What do you say? Is that true or false? True. Anybody else? Tell me all the driving forces for chemical reactions that you can recall. Gas formation, precipitation.
Weaker acid.
Yeah. Those three are usually for one type of reaction. And so are those for the redox reactions, oxidizer, reducer, redox reaction. Or are those for the double replacement reactions? They're for the... Yeah, it's false. Stronger oxidizer to weaker oxidizers is the driving force for redox. And number two, metathesis reactions consist of favorable ion combinations. I talked about this briefly yesterday because the double replacement reactions have the form AB plus CD. But when you look at them in net ionic form, it's just ion combinations. And so we were looking at some reactions the other day. For example, you have sodium chloride plus silver nitrate. This is going to form sodium nitrate and silver chloride. Silver chloride is a solid PPT. So this would be the CE. And then the IE for this is going to be sodium ions plus chloride ions plus silver ions plus nitrate. These two are soluble salts. All sodium salts are soluble, all nitrate salts are soluble. This is a sodium and a nitrate salt, so it's soluble salt. This is an insoluble salt, so we just leave that alone. And then we get rid of the spectators in the NIE. And so we're left with the silver ions like chloride ions to precipitate out silver chloride. It doesn't matter where the chloride ions came from. So here, they came from sodium chloride. But in the lab, where did the chloride ions come from for precipitation? The hydrochloric acid, right? And so this is it. So this is the net ionic. But does this look like a double replacement? It is a double replacement reaction, but when you look at it in net ionic form, it doesn't look like a double replacement. It doesn't have to be. And so this is what we call metathesis reaction. Metathesis is just swapping the ions and seeing what happens. So metathesis reactions consist of favorable ion combinations. That's true. When we do double replacement, we swap the ions to see if it results in something favorable. Something favorable would be precipitate or weaker acid. Weaker acids are more stable than stronger acids, or gas. Three, a mole of carbon-12 atoms weighs exactly 12 grams. That's true. That's by definition. 4, if 2 grams of hydrogen is allowed to react with excess, this is supposed to be O2, then 2 grams of water is produced. So if I have 2 grams of hydrogen plus excess of oxygen, am I going to get 2 grams of water? Well, the balanced chemical equation is a mole ratio and not a mass ratio. And so 2 grams of hydrogen is actually 1 mole of hydrogen. H2 is about 2 grams per mole. So if I have a 1 mole of hydrogen, it's a 2 to 2 mole ratio, so I'm going to form 1 mole of water. You know how much 1 mole of water weighs? 18 milliliters is it, and it's going to weigh 18 grams. And so it's going to produce is 18. Well, where does all that mass come from? It comes from the oxygen. Oxygen is a lot heavier. And so this is false. The theoretical yield for reaction was 98.3 grams. The amount actually obtained was 91.5 grams. The percent yield is, can you calculate that? So the formula is, if we got 100% yield, then the theoretical yield would have been 98.3, and the actual yield would have been 98.3. And so 98.3 out of 98.3 would have given us 100%. Yes. Is it? Is that what you guys got? 93.1%. Still lost a little bit. But that's typical for a lot of reactions. We use some of the product. It's hard, like, to scrape out all the crystals out of the test tube. You know, sometimes you don't want to spend 2 hours or 3 hours getting every last little particle out of the test tube. And so you just say, forget it, you'll lose it, it's all right. So that's what happens. Number 6, what ions are present in what ratio in a solution of aqueous calcium chloride? Well, calcium chloride, chlorides are all soluble except for silver, lead, and mercury. So it's a soluble salt. Soluble salts are going to be strong electrolytes dissociate the ion. So, which one does it look? C?
I think so.
You think so too? Anybody else? C is correct. Yeah, for every calcium we need 2 chlorides. And so this is what we have. Chlorine doesn't form a diatomic anion like this. Not only that, this is impossible because this is 2 plus, this is 1 minus. So the charge doesn't even balance. But here the charge is balanced, but again, it doesn't form a peroxide-like ion, Cl2, 2 minus. And chlorine doesn't form a 2 negative ion. That's monotone, it forms 1 minus. And so C is the correct answer. 7, weak acids are weak electrolytes. That's true. Weak acids, weak bases, and some heavy metal studies. HF is completely ionized in water. Well, if HF is a strong acid, it would be completely ionized in water. Is HF one of the 7 strong acids you memorized?
No.
Actually, it's weird because we have HI, HBr, HCl, but no HF. And there's a reason for that. You would expect HF to be a strong acid, but it's not. It's not in there. It's something that's discussed more in Chem 1A. And so it's a weak acid. Weak acids are only partially ionized in water, so this is false. Which of the following substances will precipitate from, well, it's supposed to be from an aqueous solution? And so which of these I'm asking is an insoluble solid? Well, we know group 1 are all soluble, so sodium salts are all soluble. Ammonium salts are all, potassium salts are all, and lead, well, excuse me. Right. Acetates and what else? Acetates, chlorates, and nitrates are all soluble. Yeah. And then we go over here. Carbonates are phosphates and chromates are all insoluble except for group 1 and ammonia. And so D is the only one that can precipitate copper 2 carbonate. 10. In the combustion of methane, according to the equation, how many grams of water are formed during the combustion of 4.24 grams of methane? So, if you have, excuse me, if you have some of these memorized, like carbon's 12.01, hydrogen is 101, nitrogen is 1401, oxygen is
15.9.
yeah, we'll just round it to 16.0. It's easier to remember. If you know these, then you can calculate all of these quickly. And so if I have one carbon that's 1201 and 4 hydrogens 404, and so methane is going to be 16.04 grams per mole. Water, 18.02 grams per mole. So can you calculate it and see what you get?
Would it be D?
D?
Mm.
Anybody else? Anything?
I think not E, but
You have E?
we try that.
So we have 4.24 grams. It's supposed to be 4.24 grams of methane divided by 16.04. That's going to give you 0.264 moles. And then it's a 2-to-1 ratio. So times 2 moles of water for every 1 mole of methane. And then times 18.02. Did you get the 2-to-1 ratio?
No.
Okay, that's well. The closest answer is going to be E. Although I got 9.53 and 9.526, but that would be the closest. It can be a little off, depending on what molar masses they use. How they rounded it. PCl5 can be produced by the reaction. What mass of PCl3 must be used to produce 127 grams of PCl5? Percent yield is 84.8%. Well, phosphorus I don't have memorized. So we just get off the dry table. Phosphorus is 30.97. And chlorine is 35.45. I have a chlorine number. Let me try some of these. Do number 11 and number 12. So percent yield, 84.8%. So let's first convert that into a converting factor. So that would be 84.8 grams actual yield over 100 grams theoretical yield. Okay. One mass of PCl3 must be used to produce 127 grams. Is that 127 grams, is that going to be actual yield or theoretical yield? Yeah, that's going to be actual yield. And so 127 grams of PCl5, actual yield. So we're going to have to produce more than 127 grams because we're going to lose some of it. And so how much more? Well, we're going to use this to figure it out. 100 grams of theoretical yield over 84.8 grams of actual yield. Since we're going to lose some of it, we're going to lose like 15% of this. We'll have to produce 15% more. So 127 times 100 divided by 84.8. We'll have to produce 150 grams worth of it in order to get an actual yield of 127. So we're going to lose some of it. So we want how much PCl3 needs to be used. So we'll have to do PCl5 is what we have here. So it's going to be 5 times 35.45 plus 30.97, which gives us a molar mass of 208.22 grams of PCl5 per mole PCl5. And then we look at the mole ratio here. It's a 1-to-1 mole ratio. So 1 mole of PCl3 for every 1 mole of PCl5. And then we need the molar mass for PCl3. So it's going to be 35.45 times 3 plus 30.97. 137.32. 137.32 grams PCl3 per mole. So the grams of actual yield PCl5 cancels, and the theoretical yield cancels. Moles cancel. 137.32 times 127 divided by, actually times 100. Let's do divided by 84.8 times 100 divided by 2. 98.76. So you got C? That's correct. Okay. How about 12? What do you get for 12? another stoichiometry, this dimensional analysis problem. So we have a delta H. Is this exothermic or endothermic?
It's exothermic.
Yeah, negative means exothermic. And so we're going to have 282 kilojoules of energy, so starting point. Then we could use this delta H. This delta H is for the reaction or equation as written. And so this is kilojoules for 1 mole of glucose, for 6 moles of O2, 6 moles of CO2, and 6 moles of water. And so normally the way we'd write something like this is 1 mole of glucose, C6H12O6, is going to produce 2.82 times 10 to the third kilojoules. Since energy is always positive, the negative just tells us the direction, so energy is being released. And so what we could do is we could just say produce as a product rather than consumed as reactant. Then we need to figure out the molar mass of glucose. So this will tell us how many moles of glucose. Yeah. The glucose is 6 carbons. So 6 times 1201 is 7206. 12 hydrogens, which would just be 12.12. And then 6 oxygens. So that's 6 times 16 is 96. 0.00. So this is going to give us 8, 1, 4, 10, 180. 180.18. So this is going to be 180.18 grams per mole. Glucose. And so to do the calculation, 282 divided by 2.82 times 10 to the third. Gives us 0.1 moles times 180.18. What did you get?
18.0.
Yeah. 18.0. And so 18.0 would be correct. Some people were asking what there's no sample final. So this will serve as with the multiple choice questions. You're going to have multiple choice questions from the very beginning, and then things that are more recent as well. So 13, visible light is a very small part of the entire electromagnetic spectrum. That's not true. "14. Radio waves always move slower than gamma rays.
Is the frequency tied to the speed? I think it's false. Yeah.
This is false. Radio waves move at the speed of light. Same with gamma rays. So they both move at the speed of light. What moves slower are sound waves. No, but sound waves are not electromagnetic radiation. 15. Within a continuous spectrum, there are regions of forbidden energies. If you have a continuous spectrum, that's false. Yeah. In a quantized spectrum, there are regions of forbidden energies. 16. Incandescent light bulbs produce a line spectrum. What's a line spectrum? A line spectrum would be like the hydrogen lamp. You know, only certain colors are given off. But incandescent light bulbs produce one color light. White light. White light consists of,
Every colors.
yeah, all the colors of the rainbow. So the answers don't make sense there. Two or infinite, yeah. This is supposed to be true or false. So what would you say? True or false? False. 17. Modern day scientists visualize electrons orbiting the nucleus in circular orbit. That's false. They visualize electrons in orbitals, not orbits. 18. Heisenberg's uncertainty principle means we visualize the electron position as a cloud. 19. Orbitals are the solutions to the this is supposed to be to the what orbitals are the solutions to what? What is it supposed to be?
To the pattern of electron movement.
Yeah, but it came from the physics, and there's a famous equation. So, do you remember the famous equation? Orbitals are the solutions to the Schrodinger equation. So, if orbitals are the solution to the Schrodinger equation, then it would be true. If this were a Schrodinger equation, but this doesn't make sense. 20. When L equals 1, we have the 3 p orbitals.
I want to say true.
Yeah, that's true. When L equals 0, we have the s orbital. When L equals 1, we have the p orbitals. And the p orbitals are going to have n values ranging from -1 to +1. So it would be -1, 0, and +1. So that gives us their 3 p orbitals. So this is true. 21. N equals 0 is the lowest energy level.
True.
This is false. The lowest possible n value is not 0. The lowest possible n value is not -1, it's +1. The n value is given here. Like, for example, 1s. This is the n value. This is the L value, but it's written in letter designation. This is L equals 0. So 1s orbital is an n equals 1, L equals 0 orbital. There's no such thing as a 0s orbital. 1s orbitals. 22. 2D orbitals violate quantum mechanics because L is too small. That's false. L is too big. You can't. With a D orbital, L is going to equal 2. And so if n equals 2, the max L value you can have is 1. And so the highest energy n equals 2 orbital will be 2p, not 2d. That's false. 23. The electron configuration for chromium is argon 4s2 3d4. This is supposed to be true or false. Unfortunately, it didn't come out that way.
Sorry, number 23 and 19. Sorry.
I'm sorry?
Are 19 and 23 supposed to be swapped?
Yeah, probably.
Well,
No, 19's different. And all the answers got screwed up on this. So 23 is supposed to be true or false. Is that true or false? It's false. What is the correct electron configuration for chromium?
Argon 4s1 3d5.
Yeah, argon 4s1 3d5 is correct. That's good. '24. Hund's rule states orbitals of the same energy should be filled singly with parallel spin.
True.
That's true. 25. The electron configuration for the fluoride ion is helium 2s2 2p6. That's true. Yeah. Fluorine is helium 2s2 2p5. And if it gains an electron, it fills the second shell there. So that's true. Yeah, the same as neon. Tungsten, xenon 6s2 5d4. That's supposed to be true or false? Is that true or false? So we can take a look at the periodic table. False? Okay. Tungsten is W. So we go backwards here. It would be xenon 54. 6s 2 takes us, excuse me, to 56. And then here, from 57 on, it would be what? 14. Actually, this is a 4F. So 4F and then 5F would be here. And so it'd be 6s2, 4F, 14, and then 5D, 1, 2, 3, 5D, 3. That would be tungsten, but so we're missing that. You can see it in the periodic table. Can you draw the orbital energy level diagram for the first 4 shells? And then label them with N, L, M? You can do that? Okay, that's good.
Could you give us the dashes? And then, would you have to do that helping yourself check the levels?
Yeah, it would be a blank page. And so, for example, the 1s orbital, it could be 100. And then the 2s orbital, which is 200. And then the 2p orbitals, it could be 2, 1, -1, 2, 1, 0, 2, 1, 1. Does that look familiar? And then the 3s, followed by the 3p. This will be the third shell. 3, 0, 0, 3, 1, -1, 3, 1, 0, 3, 1, 1. Followed by the 4s. And then you think the 4p comes next, but it's not the 4p. What comes after the 4s? 3d. We have 5 of those. 3d. What are they? They're the 3, 2, -2, 3, 2, -1, 3, 2, 0, 3, 2, 1, and 3, 2, 2. And then finally the 4p. Four, 1, -1, 4, 1, 0, 4, 1, 1. And so the energy would go 1s to the 2s to the 2p to the 3s to the 3p, 4s to the 3d to the 4p.
Are you going to give us like an element and ask us to fill that out based off of an element? Or are you just going to ask us to just write it out?
It's possible. I could give you an element like chromium. And you would fill it out. There was a question about chromium earlier, which is 4s1, 3d5. Something like that might be possible. So you should know how to construct an energy level diagram like this.
Will you be going up any higher than you just wrote?
No.
Because it gets kind of confusing with like the spacing, like the vertical spacing between them.
Yeah.
When it gets higher up.
Yeah, that's true. Let's take a look. You just need to know up to the 4th shell. Beyond the 4th shell, they start to get compressed, so it's not so clear of the shells. But the shells always begin with an s orbital. So the 4th shell begins with a 4s orbital. And it consists of 4p, 3d, and then 5s would be the next shell. With 5s, 5p, 4d, and then 6s would be the next shell. And so you should be able to draw just up through the 4th shell. Yeah. The 4p orbital. They have other diagrams here. This is just filling in. The spacing can be screwed up.
Switch at some point. What was that, 86 at this time? It's been
Which bond is the most polar? A is correct. The charge on alkaline earth ion is, the charge on alkaline earth ions are B, plus 2. 29, noble gases are highly reactive. False. 30, the bond between a metal and a nonmetal is likely metal and nonmetal is likely. What kind of bond? C, ionic, yeah. What is the predicted bond angle in CO2? 180. Strong bases ionize in water. I haven't gotten to that yet. But bases do not ionize, bases hydrolyze in water. 33. What is the predicted bond angle on H2O? C. What is the predicted bond angle on SO2? It'd be B. The answers, screw those out. There's a lone pair on sulfur. You have to draw out the Lewis structure to see this. If there's a lone pair on sulfur, one of the oxygens is single bonded like that. The other oxygen is double bonded like this.
It's about why they double bond twice.
Let's expand it out. Yeah, online. That's to get rid of the formal charge. The formal charge on oxygen is minus, the formal charge on sulfur is plus. And so they expanded the octet. But either will give you the same angle. It should be 120 here. What is the shape of ammonia? Trigonal pyramid. CF4 is a polar molecule. That's false. It's tetrahedral. Although the bonds are quite polar. It's going to be equal and opposite in 3 dimensions. 37. Water is a polar molecule. True. That's true. Here are some equations. Yeah. Predict products, state driving force, right to balance, CE. TIE is the total ionic equation, like I did. I just called it IE for sure. And NIE. Magnesium carbonate and hydrochloric acid. Lead 2 acetate and sodium sulfate. I know what reactions we have. Okay, this is percentage. Here's the problem. Draw a detailed orbital energy level diagram for chromium. This is it. We can get the quantum numbers for these electrons as well. This would be a 3, 2, minus 2, plus 1/2. These are all plus 1/2 spin out. The ones that would spin down are minus 1/2 electrons.
So are you going to post this on Canvas?
Yeah. I'll post this on Canvas. We have try to fix some of the answers. Yeah, in a way, yes. In a way, no. On the final, the nomenclature section would be with these. Like, for example, if I say magnesium carbonate, you'll have to write out the formula for magnesium carbonate. You're going to have some reactions on the side. Okay. All right, this is one. I have another one. We'll take a look at it later. Draw the Lewis structure for bicarbonate. Also include one 3D drawing, electron geometry, and molecular geometry. We did bicarbonate in class. So, take a look at that. All right. Any questions on that? Your test is primarily going to be multiple choice.
You can hear everything.
Yeah. So you can say whatever you
Wow.
Are you adopted like
No.
have it
Believe that.
so you're against the
Yeah,
people?
believe
Well,
that,
to the
Right.
corrupt system.
but yeah.
Okay. I see where you're going.
Let me finish up chapter 15. The solid state. This is a high temperature superconductor. It's levitating magnet. We have lots of different solids. We have plastics that consists of these long chains. Long chains are repeating units. The repeating unit is called a monomer, and so these are polymers. A whole bunch of these repeating units. And they can stretch out for extended distances, or you can stop them. Something like polyethylene. Polyethylene, they say, is an amorphous solid. It's an amorphous solid, although when you look at it, it's pretty well ordered here. But it's hard to predict, where the next, let's say, carbon atom is going to be, because the randomness of this chain. Whereas this is a crystalline solid. It's easy to predict where the next sodium ion will be. It will be right here. The next chloride will be right there. Aluminum is a crystalline solid too. This is silicon here, which is also a crystalline solid. And so we have amorphous and crystalline. Glasses are amorphous solids. You can also see it in the way of fractures. Even though the silicon looks like a glass, it's not really glass. Glasses have fractures that are more random, conchoidal fractures they call them. Crystals, when they fracture, they usually fracture along the face of the crystal. And so amorphous and crystalline solids here. And this is showing how we can cleave crystals, and this is cleaved along one of the faces. Over here, this is glass. Glass is amorphous solid, so it doesn't break along the lines. Let's see. These are fractures, conchoidal fractures. All right, so that's amorphous versus crystalline. The types of crystalline solids. Well, this can also go for amorphous solids as well. The types of solids depends on the bond. So we have ionic bonds holding the particles together. And so crystalline solids can be divided into 4 classes based on the types of forces that hold particles together. So if we have ionic bonds, that would be like sodium fluoride, calcium carbonate, silver chloride, ammonium bromide. It's going to form an ionic lattice. This is an ionic lattice here. This is sodium chloride. This is calcium carbonate. The carbonates are trigonal planar. Calciums are just the gray ones here. And so we have to pack this together in an ionic lattice. This is lead-2 sulfide over here. This is galena, the mineral galena, the lead ore. All right, and so ionic bonds hold these electrostatic attraction, loss of the charge. We also have molecular crystals. In molecular crystals, the molecules are held together by intermolecular forces. examples of this would be like ice, H2O solid, solid iodine, solid ICL. Whereas ionic bonds are quite strong, intermolecular forces are weak. These are relatively weak. That means it's not as hard to break apart ice crystals. They're pretty fragile. And so molecular solids have what we say, if it's not hard to break apart, then what we say is they have low melting point. It doesn't require much heat. And so something like ice melts at 0 degrees C, whereas sodium chloride melts at extremely high temperatures. Sulfur melts at about 100 degrees C. And when you melt it, you're just breaking apart the molecules from one another, which takes relatively small amounts of energy to molecular solids. We have covalent network solids. Covalent network solids are held together by covalent bonds. Covalent bonds would be like diamond, carbon-carbon bonds there. Quartz, silicon-oxygen bonds. Diamond and quartz have extremely high melting points. And they're really hard to break apart. And so quartz melts at about 1700 degrees C. Diamond melts at about 3500 degrees C. So very strong forces holding them together. And so it's covalent network. And then we have these are buckyballs. Buckyballs, inside the ball itself are covalent bonds, but between the balls are just molecular, intermolecular forces. Here's some more covalent network solids. And so let's summarize this here. All the metallic, we didn't talk about metallic. Metallic has metallic bonds. Metallic bonds have a wide range. Some metals are strongly bonded to one another, like platinum, and has very high melting point. Other metal atoms are weakly bonded to one another, like lithium or sodium. Those have very low melting points, so it's a wide range. The metals, okay, so what in the summary are we looking at? We're looking at melting point. The higher the melting point, the stronger the force. We're looking at solubility. Typically, with solubility, the stronger the bonds, the less soluble it is. But these, oddly enough, have strong bonds, but are quite soluble. Potassium nitrate, sodium chloride, maybe. Magnesium oxide is insoluble, has +2, -2, so it's a much stronger ionic bond. But KNO3 and sodium chloride are soluble. So both of those are high melting. In general, they're water soluble, but the higher the charge, the less soluble it is. Magnesium oxide insoluble. They're brittle. They conduct electricity only when heated. Molecular are low melting. Usually, molecular are nonpolar, and so they're soluble in organic solvents more than in water. Unless we have polar. We could have polar, and then it would be more soluble in water than organic solvents. A lot of organic solvents are nonpolar. And they don't conduct electricity. The particles don't have any charge. In the network covalent, we have very high melting points, and they're insoluble. You can't dissolve carbon, diamonds in water or oil. The same thing with quartz that doesn't dissolve in water or oil. A lot of these are semiconductors, but you don't need to know that. And then we have metallic. Metals are insoluble in all common solvents. Good electric conductors. All right, the last part of this chapter deals with energy and change of state. So we're going to look at some examples here. So if we take a liquid and cool it, we can freeze it. Or if we take a solid and warm it, we can melt it. So you have a liquid here, you can vaporize it, you can boil it with a gas. Or if you have a gas, you can condense it. If you go straight from a solid to a gas, it's called sublimation. Or straight from a gas to a solid, it's called deposition. And so what we're going to do is we're going to do some calculations figuring out how much energy is involved in these types of things. Yeah. So the first type of calculation we're going to be looking at are changes of state. In terms of change of state, this would be like melting, freezing, boiling, or vaporization and condensing. When we're doing with calculations with this, we have something called Q. Q is called the heat. And the typical units for Q are going to be either in kilojoules or joules or calories or kilocalories. And the equation for this is, it depends on the amount. You know, how much water are we boiling? The more water, the more heat we need. And it's going to be times delta H of the phase change. So we can predict things. So melting, we use delta H of fusion. Freezing, we use delta H of freezing. Fusion means melting in this context. Boiling, we just use delta H of vaporization. And condensation will be used to delta H of condensation. So in terms of energy, like this, let's take some H2O solid and melt it. How much heat or how much energy is it going to take to melt that H2O solid? Well, the amount of heat is going to equal the amount times delta H. In this case, we're melting, and so we're going from solid to liquid, so this is going to be delta H of fusion. And so the amount times delta H of fusion. Okay, so we can look up delta H of fusion for water. Delta H of fusion is 333 joules per gram. 333 joules per gram. So it's going to depend on how many grams of water we're trying to melt. If we just need to melt 1 gram of water, the amount of heat is going to be 333 joules. 2 grams of water will be double, and 3 grams of water triplet. The opposite can occur. That is, if I take a liquid and freeze it, then that would be equal to the amount of heat that I have to remove will be equal to the amount times delta H of freezing. Delta H of freezing is just the opposite of fusion. And so it's going to be minus 333 joules per gram. So to melt ice, I'm going to have to add 333 joules for every gram. To freeze water, I'm going to have to remove 333 joules worth of heat for every gram. And so we could remove that using a freezer. Or we could melt the ice using a stove. And so the type of calculation we'll do is, let's take a look here. This is the data, this is the water. And so we need the heat of fusion. When we melt it, the temperature has got to be 0 degrees C, that's the melting point. If we were to boil it, that's going to be delta H of vaporization, which is over here, and that's going to happen at 100 degrees C. And so something weird happens here. If I have ice, the ice is going to be at 0 degrees C, and then the liquid water here is going to be at 0 degrees C. And so all this heat goes into breaking apart the hydrogen bonds and the dispersion forces holding water molecules together in the solid. The same thing, if I freeze it, I have to get the water at 0 degrees C. So this is going to be H2O liquid at 0 degrees C. And then I'm going to freeze that into ice, H2O solid at 0 degrees C. And so when we do a phase change, there's no change in temperature. So phase change happens at constant temperature. What is that temperature? Well, it depends. You know, lead, for example, if I want to melt lead, the melting point is 327 degrees C, and the amount of energy is 23 joules. So it's a lot easier to melt lead in terms of delta H of fusion, but we need a higher temperature to do that. Aluminum, we melt aluminum at 660 degrees C, and it's going to cost us 397 joules for every gram of aluminum that we melt. Okay, so we have a melting point and heat of fusion, but we don't have freezing point and heat of freezing. The reason we don't have it is because freezing is going to happen at the same temperature as melting. And the energy for freezing is the negative of this. We have to, rather than add the energy to melt it, we have to remove the energy to freeze it. Okay, so let's take a look at some calculations here. This is, let's see, 15.3, calculating the heat of vaporization. So calculating the heat of vaporization of a substance of 241 kilojoules is required to vaporize 78.2 grams of sample. So here, they just solve the equation. Q is equal to amount times delta H. And if we want delta H, then delta H is equal to Q divided by the amount, the ratio. And so that's what they have here. The amount that they're using is in grams, so we call M for mass. But it doesn't have to be grams, sometimes it's in moles, but in this case it's in grams. And so they get 241 kilojoules divided by 78.2 grams, gives us 3.8 kilojoules per gram. Most of the time, the delta H's are given. We just calculate the amount of heat, like this. How much energy is needed to vaporize 180 grams of a liquid if its heat of vaporization is 1.13 kilojoules per gram? And so, in this particular problem, calculating the amount of heat, the heat is equal to the amount times delta H. And so 188 grams is the amount times delta H, 1.13 kilojoules per gram. That gives us 212 kilojoules. And so this is just a one-step conversion. What amount of energy is released when 2.3 kilograms of ethanol condenses from vapor phase to a liquid? For ethanol, delta H of vaporization is 0.837 kilojoules per gram. So condensation is the opposite of vaporization. So if it costs you 0.837 kilojoules per gram to vaporize it, it's going to cost you negative 0.837 kilojoules per gram to condense it. That is, we have to remove that heat rather than add that heat to condense it. And so in this particular problem, Q is equal to the amount, 2.3 kilograms times delta H. There's a problem here. And the problem here is that the units don't match. This is kilograms, this is grams. So we'll convert this into grams, which would be 2,300. And multiply for that. Calculate the heat flow when 135 grams of sodium freezes at its freezing point temperature. Express the answer in both joules and kilojoules. And so what we have to do is we have to go to the table, and take a look. We want freezing, and so freezing is the opposite of fusion. And so we'll go back and take a look at the table here. Actually, I'll just go here. And so we look for sodium metal. Here it is. Sodium metal has a melting point of 98 degrees C and a heat of fusion of 113 joules per gram. So rather than melting it, we're freezing it. And so what that means is delta H of freezing is we have to remove heat. So it's going to be exothermic. And that's going to be minus 113 joules per gram at 98 degrees C. And so if we go back to this problem here, so it says that it's freezing point temperature. So we're going to take liquid sodium at 98 degrees C and then condense it or freeze it into solid sodium at 98 degrees C. So we have 135 grams. And so here, it's Q is equal to the amount times delta H. But no, what they did here is they took the negative of the delta H of vaporization. Well, the negative of the delta H of vaporization is the delta H of freezing. And so delta H of vaporization is plus 113. Therefore, delta H of freezing is minus 113. So we have to remove that. And so we end up with minus 1.53 times 10 to the 4 joules. And then we can convert that into kilojoules, 15.3 kilojoules. Right, so those are some calculations. How much energy is needed to melt 6.3 kilograms, 6.37 kilograms of aluminum at its melting point? And so it's just equal to the amount, 6,370 grams, times delta H of fusion. Okay, the next type of calculation we're looking at is heating and warming. Heating and warming or cooling in objects. And so this is in 1510. This is heat, cool objects, no phase change. equation for this is different. Q is equal to the amount times C times delta T. Usually the amount is in grams, and so typically it's MC delta T. So some people call it M cap. You should remember the formula. So let's take a look at some of the calculations here. What C is something called the specific heat or the heat capacity. Let's say I want to warm up diamonds. If I want to warm up diamonds, it's going to cost 0.51 joules for every gram of diamond per degree C. C is something called the specific heat, and it gives us a ratio. So if I look at diamond, it's 0.51 joules of heat required to raise the temperature of 1 gram of diamond by 1 degree C. So this is the ratio. We just use dimensional analysis. If I want to heat up water, liquid water, it's 4.18 joules per gram degree C. 4.18 joules for every gram of water to warm by degree C. So the heat is going to do one of two things. When you add heat, either it's going to warm up or it's going to cause a phase change, or both in sequence. And so these are specific heats for different objects. You can see the specific heat for ice is different. So we could have ice at 0 degrees C, but if I want to have ice at minus 10 degrees C, I have to remove some heat. Here, the specific heat doesn't change. So for example, we don't put a negative sign if I'm cooling it down or warming it up. The negative sign is going to come from delta T. Delta T is equal to T final minus T initial. So for delta H's, we have to worry, is it fusion or is it freezing? Is it vaporization or is it condensation? When we have objects that we're warming or cooling, then we don't worry about changing the sign. We use the specific one as is. The change in sign is going to come from this. If we're warming it up, T final is greater than T initial. If we're cooling it down, T final is smaller than T initial. So if we're cooling it down, delta T is going to come negative, and that means we have to remove that heat. If we're warming it up, delta T comes out positive, and that means we have to add that amount of heat to do this. Okay, so we'll take a look at some calculations with this, and then we'll look at some homework calculations. Figure it out. So let's take a break now. Really dropping.
All right.
I'm telling you.
We'll get started.
It's already this bad.
In the next example here, how much energy is transferred in raising temperature? So an object warming or cooling, we use a different equation. It's going to be 475 grams of water for a pot of tea from 14 degrees C to 95 degrees C. The answer in both kilojoules and joules. All right, so the equation that we want is Q is equal to the amount M C delta T. MC delta T. So the amount is 475 grams, and then the specific heat, this is water, liquid water. So the specific heat we look up in the table, 4.18 joules per gram degree C. And then delta T, 95 is our final temperature, 14 is our initial temperature. So that's going to give us 1.6 times 10 to the fifth joules, or 1.6 times 10 squared kilojoules, 160 kilojoules. So we just plug that in. Determine the amount of energy in kilojoules needed to increase the temperature of 12.4 kilogram gold bar from 25 to 59. So this is an object of warming, and so it's going to equal the amount, 12.4 kilograms, times C. We have to look up the specific heat for gold in the table. Let's go back here. The specific heat for gold is quite small, 0.13. For metals, they have fairly low specific heat. What a low specific heat means is it warms up rapidly. A high specific heat means it warms up slowly. So metals typically warm up pretty rapidly, but things like liquid water has a high specific heat, 4.18 joules per gram degree C, which means it takes a lot of energy to warm up a gram of water by degree C. So we just plug it into the equation. We'll take a look at some problems. Okay, we'll also have problems where we're going to change the temperature. So we'll use MC delta T plus a change in state. If we change the state, Q is equal to amount times delta H. And so we'll do both in a particular problem. The way we do this is we set up what's called a heating or cooling curve. This would be a heating curve. So let's say I started off with ice at a very low temperature. And so this is going to be ice that's below 0 degrees C. Here, this is melting here, fusion. And so this is, for ice, is going to be at 0 degrees C. So if I have a cold block of ice, the first thing I have to do is warm it up to 0 degrees C. Once I get it to 0 degrees C, then any heat that's added goes into melting. And so I have to melt all the ice at 0 degrees C before I can warm it out more. And so once I melt all the ice, then the heat that's added goes into warming up the water, all the way up to 100 degrees C. At 100 degrees C, I'm going to have boiling and vaporization. When water boils, the temperature just stays at 100 degrees C. Just like when ice melts, the temperature stays at 0 degrees C. So when you have a boiling water bath, the temperature is constant as long as the water is boiling. And so all that heat doesn't go into changing its temperature. All the heat goes into boiling the water. Then we end up with steam at 100 degrees C, but we can get superheated steam by warming it up more. So that will be it. And so we have different equations for different segments of this curve. We can also go backwards. So for example, if we have superheated steam, we can cool it down to 100 and then condense it. Once all of the steam is condensed, then we can continue removing heat and cool the liquid water to 0 degrees C. At 0 degrees C, if we continue removing heat, it's going to freeze until all the water is frozen. And then if we continue removing heat, it's going to get colder. And so here, the solid warms or cools, we use Q equals MC delta T. The solid melts or freezes, we use Q is equal to amount times delta H. The liquid warms or cools, we use Q is equal to MC delta T. The liquid vaporizes or gas condenses, we use M delta H. The vaporization, delta H condensation. And heating up or cooling down the steam, MC delta T. Now the specific heats are going to vary depending on if it's solid ice, liquid water, or steam. And the delta H's vary. Okay, so let's take a look at the problem here. Calculate the heat transfer when 45.0 grams of steam initially at 111 degrees C. So we have steam at 111, 45 grams worth of liquid. It's changed to water at 25 degrees C. So we're going to cool the steam. We can't cool it all the way to 25 because what's going to happen is as we cool it, it's going to go from 111 to 100. At 100 degrees C, which is at a boiling point or a condensation point, it's going to condense until all of it condenses. And then we're going to cool the liquid water to 25. So there are going to be 1, 2, 3 steps in this. Each step requires a different equation. And what we'll do is we'll just sum up the steps. So from point A to point B, that's called steam cooling. And so from point A to point B, we use MC delta T. We look up C for steam. C for steam is 2.00 joules per gram degree C. We have 45 grams. And the temperature change is going to be T final 100 degrees C minus T initial 111. This is going to give us a negative value for kilojoules, which means we have to remove that heat. And so for the first step, we need to remove 0.99 kilojoules. Okay, then when we go from B to C, that's condensing the steam. And so from B to C, they have it equal to the amount times delta H. But it's delta H of condensation, not delta H of vaporization. So this is why they put a negative sign there. They put a negative sign there to say we have to remove that and add that. So delta H of vaporization is plus 2.26 kilojoules per gram. Delta H of condensation is minus 2.26 kilojoules per gram. And so that's going to give us minus 102 kilojoules, which is the amount of energy required. Now, the next step here, C to D, we're going to cool the liquid water. We're going to cool the liquid water just to 25. We're not going to cool it to 0, which would be its freezing point. So we're going to go from 100 to 25, T initial, T final. When we cool water, the specific is 4.18 joules per gram degree C. So this is 3 steps. And what we do is we just add up all the steps. So the first step, we have to remove 0.99 kilojoules. Second step, we have to remove 102 kilojoules. And the third step, we have to remove 14 kilojoules. So a total of 117 kilojoules needs to be removed in order to accomplish this. And so this is a multi-step calculation here. Okay, calculate the total heat transfer with 19.6 grams of ice at minus 12 degrees C heated to steam at 115 degrees C. So we have ice here at minus 12 degrees C. And we're going to warm the ice first to 0. That's when it's going to start to melt. And so the first part is warming it from minus 12 to 0. The equation for that is Q is equal to MC delta T. Once we warm all the ice to 0, then we're going to add heat to melt it. So BC here, Q is equal to the amount times delta H of fusion. Once we've melted all the ice, then it's all liquid, and we're going to warm the liquid here. This would be Q is equal to MC delta T. And then the highest we can take liquid water is to 100 degrees C, because at 100 degrees C, liquid water will start to boil. And the amount of heat here required to boil the water is going to be Q is equal to the amount times delta H. Whenever we have a delta H, the temperature doesn't change. When we have an MC delta T, the temperature changes. And so this is going to consist of 1, 2, 3, 4, 5 steps. And we'll just sum up all the steps here. And so we'll take a look at a different example. Homework.
When doing those problems, do you recommend that we always draw the heat, energy, temperature?
Yeah, the heating or the cooling curve.
Yeah.
It's helpful to do that. You don't have to do it. I mean, if you can just visualize it, what's happening. then it's not unnecessary. Um, and so some of these are just, part of just one step. How much energy is required to melt 35.4 grams of gold? Well, here we're going to assume it's at its melting point, so we don't have to warm it up. The gold melting point's not high. So normally what we have is a two-step calculation here. In this particular problem, normally we have gold at room temperature, and then we want to melt it. And so the first step here is to take gold at 25 degrees C and then heat it up to its melting point. What is the melting point of gold? Well, the melting point of gold, we look back here at the table. And get, gold here has a melting point of 1,064 degrees C. So the first point is we have to take gold at 25 degrees C. This is gold solid. And then we have to warm it all the way up to 1,064 degrees C. 1,064 degrees C. Once we warm it up to 1,064 degrees C, then it can start to melt. And the amount of energy required for melting that is 63 joules per gram. 63 joules per gram. So let's take a look at that. So, but when I read this particular problem, it doesn't say we're warming it up to room temperature. It just says how much energy is required to melt 35.4 grams of gold. And so in that case, we assume it's already at 1,064. And then in order to melt that, the temperature is going to stay constant. All that heat is going into melting that. And so in order to melt it, we're going to convert all the solid to liquid. Once we convert all the solid to liquid, then we can warm up the liquid. And so we can have molten gold, and we can warm that up until we get to the boiling point. What is the boiling point of gold? Molten gold. So let's take a look. Yeah. So if we continue heating it up to 2,856 degrees C, it'll start to boil. So 2,856 degrees C, it'll start to boil. And then all that energy is used in boiling this until we get gaseous gold. But in this particular problem, all they're asking is how much energy does it cost to melt? So we have to assume that they're already at the melting point. We don't have to warm it up. And so if that's the case, if we're just interested in melting it rather than warming this, then Q is equal to the amount times delta H of fusion. Delta H of fusion, that's the melting. The delta H of fusion is 63 joules per gram for gold. This is 63 joules per gram. And then what was the amount? Take a look at the amount. The amount of gold is 35.4 grams of gold. So 35.4 grams of gold. Grams cancel, that gives us joules. And so I don't have anything. 35.4 times 63. 2,230.2 joules. 2,230.2 joules, which is going to equal 2.23 kilojoules. And so to melt it's going to cost us 2.23 kilojoules to melt. But what if I wanted to warm up the gold from 25 degrees C? Well, that's going to cost us even more energy because we have to take the solid gold and warm it up to the melting point. And so let's take a look at it. Well, if we take the solid, then we don't want the delta H, we want the specific heat. And so do I have the specific heat of solid gold? And it is in the table here. So let's take a look at the specific heat. So if I have solid gold, the specific heat is 0.13 joules per gram degree C. So this is to melt it when the temperature is at its melting point. But let's say I had 35.4 grams of gold. And so the amount of heat here, Q is equal to the amount, or MC delta T. So this is this first step here. We're going to take it from room temperature to the melting point. And so Q is going to equal the amount. The amount is 35.4 grams times the specific heat. The specific heat of gold is very low. Yeah, what was it? 0.13. It's very low. What that means is it barely takes any heat to warm up gold. Gold warms up rapidly. Whereas water, it takes a lot more heat to warm up water. And so this is going to be 0.13 joules per gram degree C. And then delta T is T final minus T initial. T final here is going to be 1064 degrees C minus 25 degrees C. So this is a big temperature change, going from 25 to 1064. So our delta T is going to be 1039 degrees C. Okay, 1039 times 0.13 times 35.4. And this gives us 4,781 joules, or 4.78 kilojoules. So, if I had this many grams of gold at room temperature, the first thing I'd have to do is add 4.78 kilojoules of heat to warm it from 25 to 1064. Once I get it to 1064, then I add 2.23 kilojoules of heat to melt it all. Does that make sense? So in this case, it's helpful to have the heating curve or cooling curve. Okay, that's a little, but they didn't tell us that we were warming it up. They only told us we're melting it. Typically, we have to do both, warm it up and then melt it. So since typically we have to do both, then typically we draw this heating curve or cooling curve. So let's take a look at this one. Let's take a look at number 93. Number 93. A 127 gram piece of ice is removed from a refrigerator at minus 11 degrees C. So this is a very cold block of ice. It would be removed from the freezer. The freezer is very cold at minus 11 degrees C, which is sub-zero degrees C. It is placed in a bowl in which it melts and eventually warms to room temperature at 21 degrees C. Calculate the amount of energy the sample has gained from the atmosphere. So they take out this block of ice and then warm it up. So the first thing is we have ice. It's 127 grams of ice at minus 11 degrees C. So when we add heat to this, is it going to melt right away? No, it's not going to melt. In fact, in order to melt this, I have to warm it up to what temperature? Yeah, I'm going to have to warm it up to 0 degrees C. So the first step here is warming the ice. And so warming the ice, Q is equal to MC delta T. And so I need to know the amount of ice, which I have 127 grams. And then I need to know the specific heat of ice. And so I have to look that up in the table. The specific heat of ice, actually, I know 2.00 joules per gram degree C. The specific heat of ice. So it's about half of that of water. Times delta T. Well, delta T is going to be T final, which is 0 degrees C, minus T initial, minus 11 degrees C. And so that's going to be plus 11 degrees C. And so we'll have to warm up the ice by 11 degrees C and calculate that. So it's going to be 127 times 2 times 11. 2794 joules. Or 2.79 kilojoules. So the first step here is going to cost us 2.79 kilojoules. Okay, then we need to melt all the ice. So how much energy is that going to cost? All right, so once we hit 0 degrees C, then all the heat goes into melting the ice. And so for 2 here, Q is equal to the amount times delta H of fusion. And so the amount of ice that I'm going to try to melt is 127 grams. And delta H of fusion is 333 joules per gram, I recall. Just make sure. You just look that up in the table. This is a specific heat, so I need to go back. So ice melts at 0 degrees C and it has a delta H of fusion of 333 joules per gram. Grams cancel, leaves us with joules. So 127 times 333, 42,291 joules, which is going to be 42.2 9 kilojoules. I'm not allowed that. I'm only allowed 3 sig figs, I'll just carry it extra. And so to warm up the ice only cost us 2.79 kilojoules, but to melt that ice is going to cost us 42.29 kilojoules. Okay, once we melt all the ice, then it's just liquid water. And we're going to warm the liquid water up to their room temperature, which is step 3 here. We're not going to bring it all the way to boiling. What did they say room temperature was? 21 degrees C. And so the third calculation we're going to do is warming liquid water. Q is equal to mc delta T. And so the amount is 127 grams. C is 4.18 joules per gram degree C. The specific heat for water, a lot of people have this one memorized. You don't have to, it's going to be given. And then delta T is T final, which is 21 degrees C, minus T initial, which is 0 degrees C. So it's a 21 degrees C temperature increase. And so it's going to be 127 times 4.18 times 21. 11,148 joules, 11.14 kilojoules. So Q total, which is going to be the sum of everything, is going to be 2.79 plus 42.29 plus 11.14. That's 56.22 joules, kilojoules, or 56.2 kilojoules. And so that's how much heat we have to add. And that heat's going to come from the atmosphere that's the surrounding. So this is a typical calculation here. Here, pentane is not in the table, so they give us the data here. They tell us delta H of vaporization for pentane. It's 357.6 joules per gram. If that's delta H of vaporization, delta H of condensation is we have to remove that much, so it'd be negative 357.6. Delta H of fusion, here's the melting point. This melts really low. Here's the boiling point. So pentane's liquid at room temperature. Room temperature is 25 degrees C. So melt at minus 129.7 degrees C. And delta H of fusion is 116.7 joules per gram. It also freezes at the same temperature. It condenses at the same temperature. The sign changes. Specific heat doesn't matter if we heat it or cool it. Specific heat's always the same. Our delta T will be different. We can figure it out. And so those are some example calculations. Chapter 16. Look at here. Was that okay for the calculations? Yeah. Chapter 16 deals with solutions. Aqueous solutions primarily. And so when we're dealing with solutions, a solution consists of two things. The solute, which is the minor species, and the solvent, which is the major species. The characteristics of the solution are they're homogeneous. So here's a blue solution here. It's homogeneous. Solutions are homogeneous mixtures. So we're going to have a solute, the minor species, and the solvent, the major species. Here's a solute in this case, which would be crystals of copper 2 chloride. Here's a solution. Water would be the major species, the solvent. And copper 2 chloride would be the solute here. And this homogeneous mixture. Concentrated versus dilute solutions. Concentrated has lots of solute, but it's relative. What is lots of solute? Depends because of this saturation and solubility. There's a certain limit to how much solute we can put in. Some things there's no limit. Other things there's a limit. And the limit is going to be solubility. Solubility is a measure of how much solute will dissolve. Once we hit that limit, it's called a saturated solution. If we're below that limit, it's called an unsaturated solution. A supersaturated solution means we're above that limit. It's unstable, but it can happen if things have a hard time precipitating. Some things have a difficult time precipitating, and so you can end up getting more solute than what is stable in solution. Eventually, it'll precipitate out, but it takes time. In the meantime, it can be called a supersaturated solution. So some things don't have a limit. Miscible means it's infinitely soluble. And what that means is you can add as much solute as you want. There's no limit. Immiscible means they don't mix. That is, they're not soluble in one another. They're totally insoluble in each other. This is usually referring to liquids. So something like octane and water are immiscible. Octane is non-polar, water is polar. And so they don't mix. And so they're just using octane to represent gasoline here. You see it up here, water down here. These are two immiscible solids. However, octane and carbon tetrachloride mix. These are two miscible solids. Carbon tetrachloride is nonpolar, octane is nonpolar. They like each other. Like dissolves like. And so I can dissolve as much octane or as much carbon tetrachloride in each other as I want. The definition of who's the solute and who's the solvent changes. You know, there's going to be a tipping point where there's more of one than the other, and whatever species is in greater amounts, we call the solvent. Up here is a supersaturated solution. What happens is crystallization is sluggish. And this is called a C crystal. A C crystal just helps provide a template for crystal formation. And so what's happening here is they drop a C crystal in here. Right now, the crystals are having a hard time forming. Usually this happens if you have a complicated shape. For example, acetate. Sodium acetate. Acetate has a kind of complex shape with a CH3COO. The CH3C part is tetrahedral, and the COO part is triple planar. And so it has kind of a complicated shape. And in order to form a crystal, that acetate has to be perfectly aligned. And so sometimes what happens, it's a struggle to get that acetate perfectly aligned. And so what we have is crystallization sluggish. But if we provide a template for crystallization, that is, you know, in a crystal of sodium acetate, the acetates are perfectly aligned, the sodiums are. And so this just serves as a template. We could drop that in here, and then the acetates can attach, and the sodiums can attach, and crystallize out the solution. So this is supersaturated. Supersaturated. Sometimes they're easy to form, sometimes they're really difficult to form. Other things that help crystallization are things like scratches on the inside surface. Stuff like that. In 16.3, we look at the formation of a solution. There are certain steps that are involved in forming a solution. And this is forming a sodium chloride solution. The first step is we have to break apart the sodium chloride lattice. And so the sodium chloride lattice is a solute, so we've got to break that apart. And the second step is we have to break apart the solvent molecules to make room for sodium ions here and chloride ions here. And so we break the solute apart, then we break the solvent apart. And then the third step is we form solute-solvent interactions. These solute interactions are called hydration spheres, okay, so solvation sphere. And so the sodium ions are hydrated by water or solvated by water molecules. When we look at the water molecules, all the negative ends are pointed towards sodium. If we look at chloride, all the positive ends of the water molecule are pointed towards chloride. So the solvation sphere here and the solvation sphere. So the energetics of this is it's going to cost you energy to break this lattice apart. It's going to cost you energy to separate the water molecules, but you're going to get energy back. You get energy back in the form of what's called ion-dipole interactions. Ion-dipole interactions can be quite favorable. So we have an ion being attracted to a dipole in water. The ion dipole can be even stronger than hydrogen bonding interactions. So this is called the solution process or the dissolution process, dissolving. We can look at based on what's happening here is we have net dissolution, that is, the salt here is dissolving. But as the concentration of the ions increases here, then there's a chance that ions can stick onto the crystals and crystallize. What's going to happen, though, is we're going to reach a point where the dissolution rate is equal to the crystallization rate, and we have a dynamic equilibrium here. Dynamic equilibrium is we've saturated. And so this is unsaturated, this has become saturated. We're not going to be able to dissolve anymore. It's a dynamic equilibrium because it continues to dissolve, but for every one that dissolves, we have one that crystallizes. So there's no net change that's occurring here. Dynamic equilibrium. The factors that determine solubility are, how hard is it to break things apart? Or we got to look at intermolecular forces and other things. Partial pressure of solid gas over liquid solution. Temperature. Those kinds of things. So if we look at antifreeze, which is ethylene glycol here, ethylene glycol is quite polar. Ethylene glycol has these OH groups here, which can hydrogen bond with one another, or they can hydrogen bond with water. And so ethylene glycol mixes. In fact, ethylene glycol is miscible in water. Because like dissolves like, you have a lot of hydrogen bonding interactions here. Water has a lot of hydrogen bonding interactions. And so ethylene glycol is water-like. And so it's like mixing water with water. Whereas over here, oil and water don't mix. The water is not going to make room for the oil. So those are immiscible. This is an example of a gaseous solute. A gaseous solute would be CO2 in water. CO2 is not very soluble in water, but we can increase the solubility of CO2 in water. by putting pure CO2 in here. If we have 1 atmosphere of CO2 gas here, it's going to force CO2 into the aqueous state. And it's going to saturate it because eventually what's going to happen is we're going to have a dissolving rate or dissolution rate that's equal to the outgassing rate, that is converting it from CO2 aqueous to CO2 gas. If we open this to air, do you know what the pressure of CO2 in air is? CO2 in air. .3 millimeters of mercury. So we go from 1 atmosphere of CO2, because this is just pure CO2 in a carbonated beverage, to 0.3 millimeters of mercury, which is much less than an atmosphere. So when you open the bottle cap here, we end up with a supersaturated solution, because we have way too much CO2 that can be sustained in here. In other words, what's going to happen is this is supersaturated CO2. And the reason that it's supersaturated is because bubble formation is sluggish. And so one way of increasing this is shake it. If you shake this, what's going to happen? The CO2 is going to be degassed. Another way of getting bubbles to form, we like using boiling chips, like what we did in the lab. So you can drop some boiling chips in there. Again.
Is this similar to what happens to divers in the blood?
Yeah.
Nitrogen?
Right. Right. You know, at very high pressures underwater, you have air that's being forced into your blood. It has to be a very high pressure because if you're deep underwater, your whole body's being squeezed and forced down. The problem is when you go up in elevation, the pressure goes way down, and your blood is going to be supersaturated. If your blood is supersaturated, then you're going to have bubbles of gas forming.
Isn't that like divers or surf and stuff that we should be careful? What they're pressing inside the water.
Yeah, so yeah, this can be a problem. It's called the bend. Right? In fact, there's a homocomb with that. It's the same type of thing, supersaturated. There's ways to help bubble formation. One of the ways that they help bubble formation is Mentos. Have you seen that? Mentos. Yeah. Mentos or Mentos? Mentos.
You're talking about the Mentos and Coke?
Yeah, Mentos and Coke. And Diet Coke. Yeah. Mentos helps bubble formation. In fact, you have very rapid bubble formation. There are other things that help bubble formation too. Since the carbon dioxide molecules attached to the surface of Mentos light, and so that's going to help. So this is showing supersaturated. Carbonated beverages, bottling under high carbon dioxide partial pressure. And so you have like 1 atmosphere of pure CO2 here. When you open the bottle, the partial pressure of carbon dioxide above the solution drops to become equal to the atmospheric partial pressure of CO2, which is like 0.3 millimeters of mercury. Nothing. There's actually a law for this. It's called Henry's law. The higher the pressure of the partial pressure of the gas, the more you're going to force into the liquid. And so here, the partial pressure is not that high. If you compress it, you get a higher pressure and more gas dissolved. Temperature impacts solubility too. For most things, as you increase the temperature, the solubility increases. But you see some things like lithium sulfate, as you increase the temperature, the solubility actually decreases. But for most solids, increasing temperature increases solubility of the solid in water. However, for gases, if we increase the temperature of the gas, then it becomes less soluble. Gases. So these are just some general. This is the solubility of oxygen in water. And so as you increase the temperature, the solubility of oxygen goes down. We'll have less O2 in water. This is, solubility is saturated. The most you can get in there. So here they say water can hold twice the dissolved oxygen at 0 degrees C than it can at 35 degrees C. Half as much warm water. Right. So those are just some general terminology for solutions. So what we're going to do next is look at solution composition. So when we look at the composition of the solution, we have different units we can use. One is percentage concentration by mass. Mass percent. The next one is somewhere. Molarity. Molarity, we already talked about mole per liter of solution. Molarity. Molarity is really handy. The next one is molality. The molarity. Molality. Molality is optional. We'll briefly touch on it. Molality is pretty useful for certain types of solutions. The next one is normality. Normality we're going to skip entirely. Normality. Normality is used by people who do a lot of titration. Talk about normality. And then we have the summary. So let's just take a look at the summary. Well, this is solution composition. So the first one is going to be percent. It's going to either be an MM. You recall what MM stands for? Well, MM like this is molar mass. This little m over little m means mass ratio. Like it is mass of solute over mass of solution is a mass of solute over mass of solution times 100%. We also have V over V. This would be the volume of the solute over the volume of the solution times 100%. We have percent M over V. Percent M over V is the mass of solute divided by the volume of solution times 100%. So this is the first type of composition we look at. So we'll look at some calculations. The next is molarity. The molarity is equal to the moles of solute per liter of solution. Molarity. This is probably the most useful. Then we have little m. Little m is the molality. Molality has a little different definition. It's going to be moles of solute per kilogram of, not solution, per kilogram of solvent. A solution consists of both the solvent and the solute. Kilogram of solvent. Okay, then we have solution dilution, 1610. We'll talk about that. So let's look at some calculations of volume concentration. All right. So just some general questions on characteristics of solution. Mixtures of gases are always true solutions. True or false? A true solution is a homogeneous mixture. And so are gas mixtures homogeneous? Always? If they're gases, let's say foggy air. Foggy air, there's liquid droplets in there. This is the fog. But for gases like air, which is nitrogen and oxygen, it's true. It's actually true. All gases, mixtures are homogeneous solutions. And it's just the way to mix. It's mostly empty space, so you can mix them. They're miscible in one another. Two, every pure substance has a definite and fixed set of physical and chemical properties. That's true. Every pure substance does. A solution is prepared by dissolving one pure substance in another. Is it reasonable to expect that the solution will also have a definite and fixed set of properties that are different from the properties of either component? Well, this one's a bit tricky because solutions will have properties like salt water or sugar water. They'll have a distinct set of properties. But the problem with solutions is they have variable composition. You can have dilute solutions, you can have concentrated. You have unsaturated, which will be dilute, and saturated solutions, which have hit the limit. And so since the concentration varies, then that's going to change the properties. It'll be less salty or more salty depending on the concentration. And so in this case, in a way, yes, but the answer is probably no. 3, can you see particles in a solution? No, you can't. It's homogeneous, so you can't really see components. What kinds of solute particles are present in the solution of an ionic compound? In the ionic compound, the solute particles are ions, soluble salt, dissociate. In molecular compounds, the solute particles are molecules. So this is some general. Distinguish between the solute and solvent in each of the following solutions. Salt water. Salt water, the solute would be salt, and the solvent would be water. Sterling silver. And the solute here would be the minor component, so the solute would be copper dissolved in silver. So sterling silver is copper, a little bit of copper dissolved in silver. Air, we have a little bit of oxygen dissolved in nitrogen. On what do you base your distinction? Just on what's the major component, what's the minor component? You can switch. Explain why the distinction between solute and solvent is not clear for some solutions. For some solutions, they're miscible. And so the solvent and solute can reverse depending on which one is the major species. So the same thing in mixture of nitrogen and oxygen. Oxygen could be the solvent if we have a greater amount of oxygen than nitrogen. 7, would it be proper to say that a saturated solution is concentrated solution? A saturated solution has hit its limit. You can't dissolve anymore. It's maxed out. But that limit varies. For some salts that are highly insoluble, you can barely get any to dissolve. Other salts that are highly soluble, it takes a lot to saturate them. So for example, sodium chloride, it takes 36 grams to saturate it. Versus silver chloride, it takes a microgram or milligram to saturate. So it depends on the solubility. Solution A contains 10 grams of solute dissolved in 100 grams of solvent, while solution B has 5 grams of a different solute per 100 grams of solvent. Under what circumstances can solution A be classified as dilute and solution B is concentrated? It's relative to the saturation limit. So if B is less soluble, then the saturation limit is way lower than A. A takes a lot more to become saturated. And so in that case, B can be thought of as more concentrated, even though we only get 5 grams versus 10 grams. But what happens if you add a very small amount of solid salt, NaCl, to each beaker described below? Include a statement comparing the amount of solid eventually found in the beaker with the amount you added. A beaker containing saturated sodium chloride. If you have a beaker that contains saturated sodium chloride, you can't dissolve any more sodium chloride in there. It would be something like this. You have way too much salt and it will dissolve. And so if you try to add more salt to this, it's just going to fall to the bottom. A beaker with unsaturated. Well, if it's unsaturated, then you can dissolve more. It's below its saturation limit. So unsaturated will dissolve. A beaker containing supersaturated. If you add salt to a beaker containing supersaturated, then it's going to add a C crystal. And some of it will crystallize out. So just a simple laboratory test in which you can determine if the solution is unsaturated, saturated, or supersaturated. Here, you just add more solute. If it's unsaturated, it'll dissolve. If it's saturated, nothing's going to happen. If it's supersaturated, it'll crystallize. 11, in stating solubility, an important variable must be specified. What is that variable? And how does solubility of a solute usually depend on it? In stating solubility. In stating solubility, you know what the important variable is? Temperature. Temperature is and for most solids, the higher the temperature, the more soluble or the less soluble? The more soluble. But when you're dealing with gases, it becomes less soluble. Gases dissolve in water. So just units in which solubility might be expressed other than grams per 100 grams of solvent. Grams per 100 grams is just a fractional solubility. We get percent as well, but there are lots of units, moles per kilogram, moles per liter, etc. When acetic acid, a clear colorless liquid, and water makes a clear, uniform, colorless liquid results. Is acetic acid soluble in water? Yes. Is acetic acid miscible in water? It turns out acetic acid is miscible in water. Acetic acid, you can mix in all proportions. It's very water-like. It likes water. Okay, we'll skip this one here. Section 16.3, the formation of a solution. How is it that both cations and anions positively charged ions and negatively charged ions can be hydrated by the same substance, water? Well, water has a positive end and a negative end, and so it can flip. The negative end will be attracted to the positive ions. The positive end of the water is attracted. So it's a dipole. What does it mean to say that a solute particle is hydrated? What it means is it's just surrounded by water molecules. Hydration of solvated particles. That helps stabilize the solution. Explain why the dissolving process is reversible. Yeah, we could dissolve, that's called dissolution, or we could crystallize or precipitate. So it could go either way depending on the conditions. Describe the forces that promote the dissolving of a solid solute in a liquid solvent. The forces that we have to break. If we have a solid, we have to break it apart. If we have a liquid solvent, we have to break apart the liquid molecules. And then we form solvated solute. It's a break form. 19. Describe the changes that occur between the time excess solute is placed into water and the time the solution becomes saturated. The changes are you're going to have net dissolution. And initially the crystallization rate is going to be slow, but eventually the dissolution and the crystallization rate match, and that's when it becomes saturated. This is the figure reaching the dynamic equilibrium. Compare and contrast the dynamic equilibrium on both the particulate and the macroscopic level. At the macroscopic level, nothing changes. But at the particulate level, there's constant changing, constant dissolution, constant crystallization. Pay particular attention to explaining why the equilibrium is dynamic. Equilibrium is dynamic because the dissolution never stops and crystallization never stops. But it's equilibrium because there's no net change. At what time during the development of a saturated solution is the rate at which ions move from aqueous phase to solid phase? solute aqueous to solute solid greater than the rate from the solid phase to the aqueous phase. When it's supersaturated, we can get net precipitation. That's what we want to get things to precipitate. Compare the rate at which ions pass from the solid phase to the aqueous phase with the rate at which they pass from the aqueous phase to the solid phase when the solution is unsaturated. When it's unsaturated, we have net dissolution. So the solid to aqueous is going to be greater than the aqueous to solid. Why can't you prepare a supersaturated solution by adding more solute and stirring until it's dissolved? Because if it's already saturated, you aren't going to get it dissolved. Usually with a supersaturated solution, they change the conditions, like temperature. And so, for example, sodium acetate is much more soluble at high temperatures than the low temperatures. So what you do is you get it to high temperature and then cool it down. You cool it down slowly. And when you cool it down slowly, then and crystallization is sluggish, then we can form a supersaturated solution. So those are some, but mostly we're going to be looking at this type of stuff. Yeah. So factors that determine solubility. So we've got to look at like dissolves like. Which of the following solutes do you expect to be more soluble in water than in cyclohexane? Water is polar. Cyclohexane is non-polar. And so the first one is formic acid. Is this going to be more soluble in water or cyclohexane? Water. Okay. There's hydrogen bonding here and dipole here. Benzene. This is benzene here. More soluble in water or cyclohexane? Well, benzene is it polar or non-polar? Non-polar, so it's going to be more soluble in non-polar cyclohexane. Cyclohexane is non-polar. C, methylamine. Methylamine, more soluble in water or cyclohexane? Water. These hydrogen bonding interactions here, nitrogen bond to hydrogen. Tetrafluoromethane. Tetrafluoromethane is shown over here. Water or cyclohexane? Cyclohexane. This is non-polar. Which compound, glycerin or hexane, do you expect to be more miscible? Miscible means completely dissolves in water. With no limit, there's no saturation limit. So let's take a look at glycerin and hexane. So this is hexane here. This is glycerin. Which one will be more miscible? Okay, hexane is immiscible in water. This is like oil. Oil and water don't mix. Glycerin is miscible in water. You can dissolve glycerin to any extent. This is hydrogen bonding, the free hydrogen bonding there. So glycerin is very water-like, whereas hexane is not. Suppose you have a spot on some clothing and water will not take it out. If you have ethanol and cyclohexane, available, which would you choose as a more promising solvent to try? Why? Well, if water doesn't take it out, then the spot doesn't like water. And so you could try cyclohexane. Yeah, non-polar. Cyclohexane would be non-polar. Ethanol is in between the two. And so normally when we look at solubility, we look at solubility in water solubility in alcohols and solubility in like hexane is non-polar. And then we see, depending on how polar or non-polar the substance is, solid. On opening the bottle of carbonated beverage, many bubbles are released, and you hear the sound of escaping gas. This suggests that the beverage is bottled under high pressure. Yet, for safety reasons, the pressure cannot be much more than 1 atmosphere. What gas do you suppose is in the small space between the beverage and the cask of a bottle?
It's carbon dioxide.
Yeah.
I just know that.
Yeah, it says pure carbon dioxide. And this is going to be at about 1 atmosphere. It's not under high pressure for safety reasons. But it's pure CO2, so the partial pressure of CO2 is very high compared to the partial pressure of CO2 in air. Determine whether each of the following statements is true or false. A, the rate of crystallization when a solution is 2/3 saturated is higher than the rate of crystallization when the solution is 1/3 saturated. This is actually true because the more saturated, the more solute you have. The more solute you have, the higher the crystallization rate. Yeah. We'll take a look at the drawing of that. The solubility of a solid in a liquid always increases with temperature. Is that true or false? It's mostly true. Now, most solids increase solubility in liquids with temperature. There are just a few exceptions. These are mostly true. C, the solubility of a gas in a liquid increases as the partial pressure of the gas over the surface of the liquid increases. This is true. The higher the pressure of the gas, the more you're going to force into the liquid phase. This is called Henry's law. This is a simple equation for Henry's law. And now I think
You said about if there was like a question with B and it was like true or false, what would it be? Because it's technically not always.
yeah. They're saying always, and so it'd have to be false. It's not very good. This one's, if you put true, you could argue. All right, then we're looking at the concentration, the composition of these solutions. And we have percent by mass, molarity, and molality. And these are just calculations to calculate the percent by mass. There's also volume percent and over V percentages as well. So some calculations of that. And these are calculations for molarity. All right, actually we're out of time. Are we out of time? What time do we end today? 12:50. Before the holidays, I guess everybody put mind elsewhere. I was going to give you this last part. Because most people left already.
Do you want us to do this like right now?
Yeah, could you do it right now?